Hello, everyone. It is being recorded. Okay. Hello, everyone. Welcome to the Rice Computer Engineering Summer Distinguished Lecture Series. Today is our honor to have Dr. Cressler joining us. Dr. John Cressler is the Schlumberger Chair Professor at Georgia Tech. He is a pioneer in silicon-germanium HBT technology, and his group has published over 700 papers in this field. Dr. Cressler is an HBT Fellow and received Georgia Tech's top teaching award and HBT's top graduate teaching award. Let's welcome our speaker.
Wonderful. I can't hear you clapping. That's great. Thanks for joining me, everybody. It's certainly always a pleasure to appear at universities. I've not actually had the pleasure of being at Rice University, but I've been to Houston several times to visit NASA. And I hope your families and you are safe during this terrible pandemic time, and we'll all have a chance soon to meet in person. So thanks, Tayan, for inviting me. I love meeting with folks, and I know this is a virtual meeting, but next best thing. And so I'm going to talk through some things, and then at the end, I'll give you a chance to ask some questions. So we'll keep this very informal, and I promise to make this entertaining for you and that you're going to learn some things. So stay tuned with that. I've been a professor at Georgia Tech now for 18 years, and I run a fairly large research team, about 20 students. And we're broadly engaged in silicon-germanium, electronics and photonics circuits, devices, and systems. And so very broad-based from fundamental physics of devices up through applications of those devices. What I want to focus on today, though, is something that you probably haven't thought as much about, and that is the reliability of circuits and systems and the devices built from those. And I want to invite you to see this field in a little bit different way than maybe you appreciated before. And I want to broaden your understanding of what reliability means in 2020. I'm going to use silicon-germanium as an example, but any technology platform actually would fit this bill. So I want you to look at that a little differently. I think when most people think reliability, it's like, well, I want to turn on my cell phone today, and I'd like to turn it on a year from now and get the same performance from it. And that's part of it. But I think in my experience, most students don't think much about reliability of the circuits and systems they build. But you can rest assured that industry absolutely does, and they have to for a living, because if things fail in the field, then everybody is in trouble with that. So I want to come at this problem. If you're not familiar with silicon-germanium, no worries at all. I'm going to make you an expert in 5 minutes. So today I want to remind you what this technology is and where it came from and why it exists in the first place. That's useful to know because it's a very prominent leading edge platform today in many types of analog and RF systems. And then we'll talk about some of these emerging applications that interest folks like me and drive a lot of the research out there. And then I want to talk about reliability from a very broad perspective. So step back from the field, something that we worked in my team for many, many years now. Of course, industry has forever. But I want to invite folks to view that problem a little bit differently, perhaps. And once I establish that, I want to use 3 examples from my own research with direct relevance to this broader context. And that's in space radiation effects, pushing safe operating area boundaries for IC design, and cryogenic temperature operation. And at the end, of course, I will give you some takeaways to take home and to think more about. So strain engineering in the silicon material system has been around a while. And in fact, the device on your right, the silicon-germanium bipolar, is the first demonstrated silicon-based bandgap-engineered structure. The first example came in 1987. But even CMOS today, at any dimensionality below about 90 nanometers, has got strain in it. So both of these are strain-based structures. And when I say strain engineering, the idea is actually
Dr. Cressler,
yep.
Sorry for the interruption. It seems like we are seeing your web browser instead of your slides.
Show that. Now you're still seeing that?
Yep.
Okay. Let me go back slightly. I talked through, but I'll just quickly go through. So you heard me say what I'm going to do. I'll talk about the silicon-germanium technology and then a broader context for reliability, and then a few applications of that, examples. So strain engineering in silicon. So silicon-germanium HBTs, first strain engineered transistor in 1987. CMOS is strain engineered today at below nodes below 90 nanometers or so. And the idea is actually quite simple, and that is to use strain engineering, induce strain into the silicon material system as a way to improve transport properties, speed up devices, if you would, while hanging on to the manufacturability that is enjoyed in silicon and drives really our entire information age in our world. So these devices are cousins from a strain perspective. And I'm, of course, today going to focus mostly on the HBT version of that, but both are certainly relevant. Now, strain layer epi in silicon-germanium actually is a very old idea. So the bright idea, again, is to practice bandgap engineering in the silicon system. If you look on the left there, pure germanium is lattice mismatched to silicon by about 4%, which seems like a small number, but actually in the world of strain engineering is quite large. And so if you imagine wanting to mate germanium to silicon on a wafer to build integrated circuits, you're going to inevitably form defects in the process. And that effectively destroys. This idea, by the way, of combining germanium and silicon is ancient. It goes all the way back to William Shockley's 1948 transistor patent. And it actually took about almost 40 years to figure out how to do this. And the smiley face there shows how one does it. And that is if you compressively strain the germanium, silicon germanium alloy, you can get it to mate to the silicon underlying matrix in a way which is unconditionally stable and can be processed around and put onto a silicon wafer in a way that doesn't generate defects. That happened in the early 80s and took a few years to figure out how to put that inside a device, but that again took off the field in the late 80s or so. If you look on the upper right, what that does from a band structure perspective is interesting. So the silicon substrate on the right, and if you remember from your silicon semiconductor physics stuff, you've got a band degeneracy in both the conduction and valence bands in silicon. That lifts and strains silicon germanium. We have a very slight compression of the conduction band edge, but importantly, the heavy hole band lifts in the valence band by an appreciable offset. And that actually is what we're going to be using in our engineering problem. The band offsets are shown in the lower right. So we're talking modest offsets with respect to what you might see in the 3.5 world. So at about 25% germanium, we're talking about 175 milli-electron volts of band offset, which seems like a small number. But if we, as you see, compositionally grade that over a tiny distance, then we can generate enormous quasi-fields in our system. And that's what we're going to use here, as you will see. So when you figure out how to do this right, again, you introduce the silicon germanium alloy inside the silicon matrix. It's done in a pure silicon manufacturing fabrication facility. All it takes is a silicon germanium epi tool. And if you, in this case, take a detailed cross-sectional TEM image of that, you see that there really is no evidence that silicon germanium is even there. And so no obvious defect formation or yield detraction or anything that makes that difficult from a fabrication. So silicon germanium bipolars really are silicon technology, and I think that's absolutely essential to the way it's practiced in 2020. Now, I don't want to bore you with equations, but I want to make a simple point, and that is that if you look at the transistor built from this, and you may be less familiar with bipolar transistors, I'll explain what that, how that operates in a moment, but what we're doing is introducing silicon germanium alloys into a fairly conventional bipolar transistor to engineer its properties. And we're going to do that in a compositionally graded way. If you look on the lower left, you see the base region is shown there in the rectangle. And now I'm going to grade the germanium up across the base and back down in the collector region. If you look right above the energy band diagram. So if you imagine again how a bipolar transistor operates, we forward bias the emitter base junction. So I forward inject electrons from emitter to base. They drift diffuse across the base and are collected to generate a useful collector current. And then the holes are back injected, suppressed by the high doping in the emitter. So you get a finite current gain out of the device. When we add germanium to that problem, you see that the barrier that the electrons see to injection is decreased. And that exponentially translates to more collector current and hence higher gain. We have drift transport. Drift transport is enhanced by the effective field induced by the germanium grading. And we also get an improvement in the output conductance of the transistor. So these are all things that device designers and circuit practitioners care about, these ability to improve these parameters, but importantly, they're all changeable parameters, meaning we can engineer them to get the properties of the transistor that we actually want. Now, that's not a new idea, actually. So if you look at the bottom 70s, what's key here is that we're doing it in the silicon manufacturing environment, and hence bringing all of that maturity that drives that into the table. And so that's, in a nutshell, what these devices are actually doing. Now, the technologies out there have grown very rapidly. When I got into this field at the beginning of my career, transistor speed was in the 50 gigahertz range. And we thought that was blazing fast. Today, we're in the 500 to 600 gigahertz range, so 10 times higher over the last 25 years or so. So there's been tremendous growth in the performance of these platforms. That's, of course, a healthy sign of any device technology that's out there, and of course begins to enable very interesting thoughts on what one does with such high performance devices. And we'll talk more about that in a second. When one says silicon-germanium 2020, you mean implicitly that that's the bipolar transistor married to the silicon CMOS transistor for highly integrated solutions. So you got both device types presence. And if you look on the right-hand side, you can see that these silicon-based technologies are very complicated to look at. If you look at the orange box, that's the HBT, and the blue and the green are the CMOS transistors. So complicated, yes, but absolutely routine from a silicon perspective these days. So that all that superstructure is classical CMOS back end of the line. There's nothing particularly new there. And so this really, again, is a silicon-based technology. Now, it's useful to compare these devices to other devices, and don't push this type of comparison very hard. It's always fraught with interpretation latitude. But what I wanted to do is kind of show you where silicon-germanium fits into the puzzle. The first thing to say is that the 3.5 transistors are always going to have superior performance to silicon-based transistors because they have better material systems to work with, higher transport parameters, better transport parameters. But as I'm sure you know, the world is silicon-based. It's why you have an internet. It's why you carry a cell phone. And in present, if you count numbers, there's about 10 to the 22nd silicon-based transistors that have been shipped and are out and deployed in the world, which is a staggering number to think about, right? More than the stars in the sky in the deep years. So one of the great triumphs of human civilization, I think. So the bipolar transistor, because it is a bipolar transistor, has some nice attributes. It has very nice noise properties. It has very high transconductance per unit area. The CMOS doesn't enjoy that favor, but of course it has great integration capabilities and great yield properties. And so the idea here in silicon-germanium by CMOS is to marry both of those together and let them do what they're best at, right? So CMOS for digital types of things and control logic, for instance, or DSP, and the HBT for analog and RF functionality, where it generally enjoys performance advantage at fixed scaling node. So that's the idea. Hang on to silicon, but bring it all to the table. So low cost, reliable, high yield, extreme levels of integration with extremely high levels of performance in 2020, as you will see in a moment. And that's, again, not to diss on 3.5. If you want, watts of power out at millimeter wave, GaN's your choice, right? But there's lots of applications which can range up into the 100 to 200 gigahertz application frequency that can be satisfied by these silicon-germanium platforms, even though they're low voltage, as you will see. So if you think of where does this technology fit in the scheme of the world, it's really an ideal fit for performance-constrained analog ICs and RF through millimeter wave ICs. That's where it's being developed and deployed and used and manufactured, and you see it all over the place, all the way from your smartphone into your broadband internet and things like that, right? I say performance constrained because there is some cost adder to putting silicon-germanium in these platforms. Typically, 15, 20% cost adder, but it gives you more performance, and you need that for many of these applications. And of course, these technologies are under innovation as we speak. So there's no robust technology out there today of any flavor that doesn't continue to evolve. So in the silicon-germanium world, we have enhanced germanium profiles, new device structures, laser annealing, rotated wafers through silicon via, MEMS, integrated photonics. All of these are being brought to the table with these types of technologies as the lithographic nodes scale forward. So that's kind of what you would expect, and it's exactly what you see. You could logically ask what the limits or boundaries of speed in these types of devices are. A couple of useful merits to benchmark that from an RF perspective would be the fmax and the FT, the unity gain cutoff frequency and the unity power gain cutoff frequency, fmax. Plot those on each other, you kind of get a good sense of where small signal transistor performance sits. And actually, the world record for silicon-germanium still sits at 4.3 Kelvin, by the way, measured in my lab, I'm proud to say, at 800 gigahertz of fmax counting. So extreme levels of performance. My own sense is that FT and fmax above a terahertz is clearly theoretically possible, and I think you will see that quite soon. And compared to CMOS, you can do that at very modest lithographic nodes. So the 4.3 Kelvin result at 800 gigahertz is actually 130 nanometer platform. And so think terahertz of performance at room temperature with what seems like very small voltage levels, and they are about 1.5 volts of BVCEO, and maybe 3 times that for BVCBO. But those are coming, and you will see those shortly. Lots of people working down that path. Now, you could legitimately ask, do I need that much performance in a transistor? And the answer to that depends. So some applications at millimeter wave do need that level of performance at that high frequency capability. But it's important to appreciate that the ream of lower frequency applications, say down in the, 2 to 50 gigahertz range, can benefit from trading raw performance for metrics that one cares about, say power dissipation or noise performance or linearity, et cetera. So this enduring power of silicon, which I'm sure doesn't escape you, these are some examples of, I'll call them subsystems that came out of my team, ranging from 100 gigahertz radar TR modules to data converters to space instruments, radiometers there. And I think, so you can do lots of things in these silicon-germanium by CMOS platforms. Each of these, as you might imagine, will fit on your thumbnail, right? So we're talking extreme levels of integration, and that really is the power of silicon, to do that at volume, reliably, at low cost. So the types of emerging opportunities that we think about include radar, comm, imaging, remote sensing, integrated photonics, and something my team has historically specialized in and driven, and that is extreme environment electronics. That is ranges of operation that lie beyond what people would typically think about doing on the Earth. And I'll give you some examples in a second. And this is driving a lot of research, including mine, all of these things. Millimeter wave is a hot topic. Think frequencies of operation from 30 to 300 gigahertz. We have evolved to the point today where we can actually think about those types of applications embodied in silicon-based systems. And again, because those are low cost and highly integrated, you can do lots of interesting things as we look forward. And so there's a lot of focus on understanding how to build at millimeter wave and what to do with those things. Remote sensing systems, various communication things, lots of obvious choices there that may have volume and drive markets downstream. But we're still kind of in the stage of figuring out how to best do it, which makes it fun. One sweet spot for our team is silicon-germanium radiometers. Think of that as just an ultra-low noise receiver. We want to put that on a CubeSat. So if you look at the figure on the left, where it's up above the Earth's surface, looking down and measuring noise, basically, which it converts back to temperature. And so it's ideal for climate science, which of course is important in our world of climate catastrophe. That's been the missing link for most climate models, would be real-time temperature, global temperature data. This kind of thing can provide that if you put it up as a constellation, and that's the vision. This window from space at V-band, 50 to 60 gigahertz, translates into a radiometer on a chip shown at the bottom of about 2 square millimeters. And so think about that. You got a very sophisticated scientific instrument that fits in 2 square millimeters, and hence very obviously can go into CubeSats for deployable constellations. And that's a model that we're working on with folks. I'll sidestep and talk a little bit about photonics because that's another area of great interest these days, and certainly in my team as well. And that is, if you look at what's called the terahertz gap in the electronics world, it's tough to generate power up in the terahertz regime. You just can't get much out of that. And of course, you move to optics, you can do that more efficiently as you go up in frequency. But the idea is, can we put silicon-germanium in that so-called terahertz gap? I stole this from somebody, but I love the terminology. Fill in the terahertz gap. Having a lot of work these days, and that's known as integrated photonics or integrated silicon-based photonics. And so think of that as joining electronics, what I'm mostly talking about today, with photonics on a silicon die, which uses germanium detectors. So it is a silicon-germanium system. And putting those together monolithically, or if not monolithically, then in two separate chips into a package. And that's an extremely high growth area with lots of potential for doing interesting research and actively engaged. So that's you're now officially an expert in silicon germanium. You know where it came from, why it does what it does, what's the motivation, what do you use it for, what drives research today. And so keep that in mind. And now I want to kind of look in a little more carefully at this broader context of reliability, and then we'll talk through some examples, illustrate ideas. So here's my semi-private view of the world, but I think it's a fair one in my experience. And here is a picture of how most device or fabrication engineers, people that build IC technology, what they think of circuit designers. And what they think of them is that this very complicated widget-based circuit schematic gets translated through some serious black magic into an IC which we sell. But they have very little clue of how that actually happens, in my experience. At the same time, most circuit designers, so they don't get off the hook either, a circuit designer's impression of device and fab engineers' jobs kind of looks like this, historically at least, and that it's a black box. You know, a transistor, I don't really care what it looks like or what it is, as long as I know what its input and output characteristics are. And so that's kind of avoids knowing what technology is and how you build transistors and operate those, right? And that's not a great scenario either. So in my view, there is what I call the great divide, and that is you have technology which builds integrated circuits, devices which are built from that technology in a very carefully architected way, and then the circuits built from those devices, ultimately that are configured into systems and sold, right? So the problem, and what I'm arguing against here, is that that tends to be confined to three different worlds in three different languages. They don't understand each other very well and what their constraints and needs and takeaways are. And I will argue forcefully here that that needs to change if we're going to make progress moving forward. Now, when things go bad, and they always go bad, in my experience, this is the way it works. So the circuit designer makes his measurements of his circuits he crafted so lovingly, they don't work as advertised. And so they, of course, look over to the poor helpless puppy in the device camp and they say, you screwed up the devices and your devices are screwing up my circuit. Fix them. And then, of course, the device person looks at the technology person and says, hey, your technology's out of whack. You're screwing up my devices and my devices are screwing up the circuits. Fix them. So that's kind of the way it often happens. But it's important to remember it's the circuits and systems that pay the bills, right? So technology underlies it all. The devices underlie that at one layer of abstraction higher, and the circuits and systems, of course, pay the bill. And so the point I'm making here is that as we look these days and looking certainly forward into the future, this technology to device to circuit coupling is getting much stronger. And that's especially true as technology nodes decrease, scaling wise, and also true as operational frequencies increase. So that coupling between the three actually is growing far stronger over time. And get them talking together using the same languages and developing will bear fruit, albeit any more effective. Certainly less so as we move forward in time. Added to that sophistication of need between the communities is the desire by application folks to operate our electronics in new environments. And so If you think again of reliability in a general sense, that we want the thing to behave tomorrow as well as it did today, putting it in a new environment potentially puts that reliability at risk. And a perfect example of that is flying things in space. You know, the world is moving much of its infrastructure into the space environment, and that has all sorts of interesting side stories to it. But radiation is inevitably faced here, right? So, and that comes in three different really varieties that we are concerned about. If you look on the lower left, you've at least heard of the Van Allen radiation belts. These are belts which basically are trapped particles, high energy particles from the solar wind. They get trapped in our magnetosphere. And of course, any satellite orbiting the Earth has to fly through those. And when I say radiation, lots of radiation. So just as a side note, in a typical low Earth orbit, which is the most benign case for Earth, we're talking over a 10-year lifetime, maybe 100 kilorads of radiation, total dose radiation, 100,000 rads. It only takes a few hundred rads to kill a human, right? So we're exposing our electronics and photonic systems to lots of wicked radiation up in orbit. That comes in three flavors: total ionizing dose, think charged particles or photons, right? Displacement damage, where you have some sort of ion which is going to move things around in your lattice, and then single event phenomena, where you have a deeply penetrating particle that can't be shielded, right? Cosmic rays, for instance, would need a foot of lead to shield, and you're not going to fly lead up into space. So these little thin shells of our spacecraft allow them to penetrate right through the IC and do lots of things, leading from something benign like bit flips to something catastrophic like latch up and death. So those are all real phenomena that one deals with in space. In a different context, where environment can increasingly affect reliability, is the temperature map, right? So we think of building electronics for room temperature, but of course, nobody builds electronics just for room temperature, because applications span many ranges, right? So the mil spec is from plus 120 C to minus 55 C, or 218 Kelvin, and you can see that's where most designs are done, but space exploration takes that temperature far lower. Some of the outer planets are down in the 50 to 70 Kelvin range on their surfaces. If you move down into the milli-Kelvin domain, is a very hot topic these days with respect to quantum science, quantum computing, quantum communication. Those need very low temperatures to work, and hence our electronics is going to be called upon to operate over a wide variety of environments that can potentially do harm to them. So we have to understand that and broaden our perspective. So a one slide snapshot of what I'm arguing from a reliability perspective is that we need, going forward, to have a coordinated, more expansive view of reliability in general as it relates to integrated circuits. So that involves technology, devices, and circuits simultaneously, not taken in isolation where they historically have been, and bracketing that on both sides by the operating environment, which may be particularly wicked in how that affects the reliability, because ultimately what we desire is the same thing, and that is reliable systems at the end of the day. I power it on a year from now, it behaves exactly like it did today. So closing the reliability circle, and this again kind of is a look back at historically how industry has attacked this problem and why it's problematic in the model that I just argued. So whether we're in space or whether we're doing electrical stress for aging, we have some damage source associated with the operating circuit in question. And that manifests itself in physical damage, which we attempt to understand the physical mechanisms. And then if you look traced clockwise there down to the electrical manifestation, the transistor properties will begin to shift or age as a response to that stress or reliability constraint that we've faced under that. But when I say closing the circle, what we really need to do is follow that beyond the device level, which is where industry largely has stopped over time until recently, and move that into the circuit domain, because ultimately the circuit domain is what we care about. And so if you close that circle, what that brings to the table is really the mantra of my research team, and that is look or focus on device to circuit interactions to really get a fuller and more complete picture of what's going on, and importantly, how one mitigates various sophisticated phenomena. Great. So let me zoom in now a little bit more and hopefully not blow you out of the water. but get a sense of a couple of things. One, the reliability of the bipolar transistor is complex, without question. Always has been, and it's gotten more complex over time. And I'm showing on the left-hand side just a schematic, emitter on the top, collector on the bottom, base contacts to the right. And now I'm imagining flowing current through the device. In the collector-base junction under sufficiently high collector-base voltage sees high field. We have a probability of impact ionizing the lattice in that high field, and those have some probability of making it to these EB spacer oxide, which can produce trap states at that silicon-silicon dioxide interface by depassivating bonds. And that manifests itself in a recombination current, which you see on the right, which will degrade your base current over time. So if I'm in that stress regime, which is pretty easy to reach in modern devices, my base current is increasing as a function of stress time, and that of course is decreasing my current gain, which is typically undesirable. Right? That's been the classical failure mechanism of bipolar transistors themselves, but it's much more nuanced than that. Very complicated problem. Now, from a circuit design perspective, one typically talks about safe operating area, SOA. If you're not familiar with that acronym, you should be. It's a very common phrase. Right? It's very simple to understand. What it basically says on the bottom there is, and I'm going to plot output current, collector current as a function of collector voltage, and look at where I'm actually biasing my transistor. How much voltage do I have across it? How much current is going through it? And is it safe to do that? The regions where it is safe to do is called the safe operating area, right? It's kind of not too creative, but it's kind of descriptive, I think. So that's what it looks like in a real bipolar transistor. I've superposed there a dynamic load line as a device is switching inside a circuit, just so that you can see this. But the first thing to say about the silicon-germanium picture is that the damage space, the aging stress space, is nuanced and complex. And you see 4 different regions where bad things can happen. You have mixed mode stress, which is typically high voltage, medium-sized currents, high current stress, which is low voltage, very high currents, and annealing region in between, and then ultimately the hard fail limit out on the right-hand side that could either be electromigration induced or just junction induced. So what happens to circuit designers when they build technology and they construct devices, they come in measuring transistors and they specify that safe operating area boundary. And of course, if you can imagine for a moment, if I'm a technologist, I want to be pretty conservative with that number, because if I'm not conservative, then people may go across that boundary and actually their circuits are not going to be reliable, and you'll catch hell for that, right? So that's not a good thing. But it's important to appreciate this sort of single curve SOA is a ridiculously oversimplistic problem. What industry has classically done is to take a one-size-fits-all to apply all devices in all situations, and that clearly is not the case. The other thing to say is, if you look at the blue arrow, there's a substantial window of opportunity. I call it reliability headroom between the actual SOA boundary and where the device gives up its life and fails, right? So, and you could say, well, it's nice to have a boundary there, but effectively what you're doing by staying way too conservative on the SOA is to throw away device performance. And that translates to circuit and system performance. So inevitably, it's a reliability versus performance trade-off that one has to engage. And so it becomes important. And so the idea is that we've been exploring is, can we live in that intermediate land between classically DC specified SOA and hard failures? And can we exploit that for circuits? And the answer is yes. And I'll show you an example of that. High current versus mixed mode. These are 2 different bias regimes for the transistor on that output plane. And you can see the red is bad. That's very high field, very high impact ionization generation in the CB junction. So you would expect that to have some reliability problems, and it does. But notice on the right-hand side, the high current effect, now the high field region is pushed down into the collector by high current injection effects in the device. But now up near the EB junction, you see the heavy blue region is actually evidence of a different mechanism going on for degradation. And it has a different T dependence. So now I can have, depending on whether I'm dynamically biasing in one of the 2 regions, I have not only two different operative mechanisms that behave differently, but they have different T dependencies. And I may switch through those dynamically with some sort of duty cycle. So it becomes very complex and nuanced. And that's exactly where we like to live, in that nuanced land. So from a circuit design perspective, what you really desire is something in the compact model domain. And compact model would be, what if I'm doing a cadence-based design of an IC, the compact model is the transistor model that I create what I'll call a reliability aware model, which has a number of advantages. And just think about what you're doing for a moment and why it's so useful. Classically, that doesn't exist when we do circuit design. And so if you asked any circuit designer, particularly you students, is your circuit going to be reliable? All you could really say is, well, I didn't exceed the safe operating area, so it must be reliable. But that's an inference. And you've also very likely, if you stayed in that boundary, you've thrown away performance of the circuit itself. Wouldn't it be cool instead if I had a model which, when I was done with my nominal design, I could swap in and run what it's going to look like 10 years later from a reliability perspective. And then I get a very quick idea of what matters and what doesn't. And I'm able to come back now iteratively and do a more robust, higher performance design, which still in principle is reliable in system usage. And that's been a holy grail, if you would, for a long, long time, and one that my team is working toward, has been for a few years, and are still working toward. But you can see the amplifier on the left. You can now come in and swap in these reliability models and begin to look at what the aging happens in the information. We're not there yet, but we're getting close to that. So let's take a deep breath. Hopefully you're still with me. I can't see you, but I'm assuming you're still there. And I want to give you some examples that bear out this argument I made about the broader context. That is, this tight coupling between technology, devices, and circuits to get things done. I'm going to use three examples which are very prominent in my team and we've been active in for a number of years, and that is space radiation, things that lie in space, cryogenic temperatures for quantum stuff, and pushing SOA boundaries for improved circuit design. So I'm a teacher out there, and if you've gone very far in your research careers, you will know that that conventional wisdom is often arrived at after lots of experience, and so there's things that you often will hear. So what your teachers will always say in the context of these devices is never expose them to radiation because they're going to fall apart, never operate upside down, flip the emitter with the collector, never saturate it because that's a terrible thing to do. Always obey the transistor SOA limits in the PDK, the process design kit, the circuit design kit. Always keep your transistor warm and cozy, but not too warm and cozy, because otherwise, budding researchers that are students is to always feel empowered to go back, stop listening to your teachers, and critically reevaluate whether these conventional wisdoms are true for the types of technologies that we're engaged in as we speak. And the answer in many cases is no, they're not. I'm going to give you 3 examples. So the conventional wisdom with respect to bipolar transistors in space is that they are known to be total ionizing dose soft, meaning they degrade rapidly in space. You see rapid junction degradation with increasing dose as you accumulate orbits. You bring low dose phenomena to the table that you see in space, which is a mess. And the moral to the story is death and destruction await you. So please stay away from radiation. Don't fly bipolars into space. Well, that's the kind of challenge I needed in my early career to violate that conventional wisdom. So kind of on a dare, we went out and looked at the space radiation capabilities of silicon-germanium bipolar device 596. And that is they don't degrade. So the conventional wisdom was wrong. I'm showing the current voltage characteristics on the left, the small signal cutoff frequency on the right. And I'm taking this now to, it's on a proton beam, but up to multi-megarads of total ionizing dose exposure, which is more than you would ever see in Earth orbit. And you don't see much change in the DC or AC properties of the device. And that's without any intentional hardening. So we just took a terrestrial technology, exposed it to wicked levels of radiation, and everything looks just fine. That was jaw-dropping then, and it's actually kind of jaw-dropping now in the space system, because it's a beautiful thing. Now, you might logically say, why is it? And it turns out not to be due to the germanium. and that's kind of interesting. I'd love to say it's a germanium effect, but it's actually not. It's the epitaxial-based structure used to build that device. And you can prove that quite simply by removing the germanium from a technology, and you still see that it's total dose hard. So it's got a lot of advantages for space, and that suggests applications, of course. Turns out that it's not that friendly, however. If you look on the right-hand side, at a cross-section of the device, you have a heavy ion from space that you can't shield in your spacecraft, punctures right through the device, depositing high densities of electron and holes. Those are sucked into the device terminals. You get transient phenomena on your EBC terminals, and currents and voltages move all over the place, and that translates to bad things. That's classically replicated on the left-hand side, where we're plotting error cross-section. Think bit flips as a function of what's called LET, which is just charge per unit path length for the ion. And what you really would like is what's shown in purple there, and that is a finite LET, maybe 10 would be great for orbits, and a low saturated error cross-section. And what you see is exactly the opposite. And so that was kind of bad news. So it's total dose hard. He, as a researcher, says, well, let's figure out why and see if we can fix it. And that's exactly what we did. So the physics of transient radiation is complicated. It takes sophisticated TCAD solutions to solve those problems. But if you look at the current on time shown on the left from the ion strike, you see multiple regions, very high transient signatures that last a long time, up in the nanosecond domain. Very complex charge dynamics moving spatially in the device, and depends on currents and voltages, impedances and geometries, et cetera, et cetera. So it's a really complex problem that's occupied us for a couple of decades now. But if you want to solve that and actually build radiation hardened silicon-germanium electronics, that can be done. And the way you approach that is this, again, technology to device to circuit type of a viewpoint of reliability to environmental changes. So you use physics from TCAD to get at what's actually going on. You embed that into circuit simulations so that you can actually understand what's happening, and then build better circuits to self-mitigate or mitigate those phenomena. And then you go to a radiation test facility and actually verify that. We've done that hundreds of times, literally. I'll show you one early example of success from the early 2000s, and that is to show that you can mitigate the soft errors in silicon-germanium. If you look at the circle blue there with the purple arrow, those ones with downward pointing arrows are meaning error-free. So we pulled out all the stops of learning at the device and technology, hardened silicon-germanium for that. Now, that didn't mean the subject is closed at that point. We're still working on that. More recently, we've become interested in single event transients in RF systems, because most CubeSats, small sats, big sats have RF communication links. And so I show a transceiver in the middle there. If you imagine this ion strike hitting, say, the low noise amplifier, the LNA, you can get both magnitude and phase distortion of that signal, and can cause all sorts of wicked things. That most benign case, that can cause data loss due to the constellation movement of the IQ diagram. And it's difficult to monitor, it's complex to interpret. And of course, we ask these very simple questions. Can we solve these problems, right? And we push down that path. So that's an example from space. Technology, devices, circuits, all those kind of fit into the same picture to enable that type of operation. That's happening, by the way. There's lots of people putting things up in space using a lot of the ideas that we have worked to understand. Another conventional wisdom is to stay away from SOA boundaries. So if you're a circuit designer, that says, the conventional wisdom says, believe everything the manual says, right? That is, don't push your devices beyond the SOA limits, because death and destruction await beyond those boundaries. So stay away from those boundaries. But if you look at the data-based plot and below that, you see that there's a large difference in I and V between the SOA boundary in magenta and the hard fail limit there. So we want to see what happens in that process. So lots of interesting questions. We've focused on this mostly from an RF perspective. So think power amplifier and low noise amplifier. I'm showing just a hypothetical cascode amplifier. This is an X-band PA. You could ask all sorts of interesting reliability questions. You know, how much voltage can I put on that collector swing of the output stage? How does the bias circuitry get coupled into these phenomena? How much voltage can I handle on the front end? What are the electrothermal interactions that may be going on if I'm pushing a lot of current through this device? So lots of interesting RF reliability questions. And this gets down to the device level and ultimately down to the technology level. So the first takeaway that we learned, quite interestingly, is that device damage is not equal to circuit damage. And that has very important implications if you stop and think about this. So we took a real X-band power amplifier and started doing bad things to it, biasing it in ways it was never intended to operate. And what you can see is if you plot the collector and, the current on voltage on the right-hand side there, and you look at the stress time and look at that upper device in the cascade stage, you see that it begins to grade very rapidly with these extreme conditions of bias on the device. And you might say, well, what a disaster that is. But it turns out in the cascade topology that the gain stage is what drives most of those parameters in this amplifier configuration. And it really didn't change at all. And so you had then a PA with zero change to its S parameters and zero change to its large signal parameters, and yet had a increasingly leaky upper stage of the device. So you could say, well, what matters? Well, if I'm specifying my reliability from the device, I've way over specified it with respect to what's happening in the circuit itself. And so that was a good pointer early on for us that we could play some games with circuit design. That's kind of where we went. To understand why DC and RF are so different, this shows a very nice and compelling plot on the story here. So if you look on the lower right, this is the output plane of a device inside a circuit, and it's got a dynamic load line, and the green dot there is where we're going to bias this thing. We're going to let that either be a DC bias or we're going to let it be the dynamic bias as the circuit's operating. What you see on the DC on the left and the TCAD simulations in the middle, I'm plotting impact ionization rates, think reliability problems. Red is bad there. And so between the DC and the RF, you see a large difference in the impact ionization rates between the DC and RF configurations. And there's some subtleties associated with that. But if you look on the upper right, the hot carrier generation rate is about an order of magnitude lower in the RF sense. And that translates into far improved reliability for the circuit than it did for the device. Now, the problem is that most of industry specifies their SOA and reliability from DC measurements. And so it's very clear then that those are generally very over-conservative with respect to what one can get away with, and hence they're throwing away performance that can be done reliably. And that matters. This shows a nice view, kind of the apex of mixed mode TCAD. So I'm running TCAD to look inside the device while the circuit is actually operating. Again, this Cascode PA running at 10 gigahertz, current density on the upper time sequence and electric field on the lower time sequence. And you can see it's switching. Each picture is a different time step as it's moving through its dynamic load lines. That's kind of a really neat picture. But if you look at the lower right, you see whole regions of operation where not much is going on. Blue is good in this case, right? And so that led us to believe that we could play some games with biasing beyond what a PDK might actually tell you is doable. And so we built a W-band PA. You'll notice on the right-hand side that we're swinging above the BVCVO of the device, which is classically nobody in their right mind would do, but you can actually get away with that. And we got away with that by looking at the detailed physics of the device, which is tied to the technology. So that, again, this technology device. We built that. It had at the time, this is 5 or 6 years old now, had record performance at 100 gigahertz, 40% power edit efficiency, and about 20 dBm saturated power. So world class result, done by understanding the reliability and its nuances. Last topic I want to talk about is this conventional wisdom that says believe everything that the PDK says and don't push your devices below minus 55 C, because that's the bottom temperature that technologies are specified. And if you do that, death and destruction are going to await. So stay away from cryogenic temperatures. Well, this goes back early in my career because I kind of cut my teeth as a young researcher in cryogenic operation of these devices. And if you go back and look at the basic physics of the silicon-germanium HBT, you actually expect that physics to drive far better performance as you decrease the operating temperature due to a variety of favorable things. But in essence, as the temperature drops, all the parameters you care about improve. And so it's a very natural low temperature device, and hence one of the reasons people are looking at it for for quantum science. So again, just a reminder that 800 gigahertz at 4 Kelvin is the performance record. We've actually operated these devices down into the millikelvin domain, and it's got some nuances I will show you in a second. So you might wonder logically how millikelvins are done, but millikelvins is the land of qubits. And so if you want to build interface amplifiers and electronics, they've got to operate at very low power, and they have to be at extremely low temperatures down in the millikelvin. This shows us state-of-the-art silicon-germanium HBT on the left, the IV characteristics, and then the current gain and transconductance on the right. You see that it operates very nicely down to 70 millikelvin, but there is nuanced physics there, which makes it quite interesting. DC characteristics below about 40 Kelvin kind of quench and don't change a whole lot. And what's going on there is new transport physics, which in principle can have implications for circuits. And so this is kind of interesting. It's a fairly new field for us. Cryogenics isn't, but looking at millikelvin domains, there's a lot of richness to that topic, including circuit design. But there are reliability concerns, ones that have that are driven by the physics of the device and the technology underlying it, which also have circuit implications. And I'm going back now and measuring lots of different devices. And you see as you go down in temperature to 7 Kelvin, the error bars of scatter of those device parameters, the IC and IB increase in variability. So if you look at the variability and plot sigma over mu and percent, you see large changes in DC variability as I go down in temperature. Which, if you think about an analog circuit, for instance, which might depend upon device-to-device matching, that's a serious issue. If you quantify that, the cryogenic parameter variability, DC variability is much larger than the RF variability. That's good from a circuit perspective, but still worrisome from a bias perspective. Something that's got to be A, understood, and B, modeled. And so we've done that, and this traces back to the underlying physics of the device, both the p-n junction physics and the germanium coupling to that as the temperature swings. So it's fundamental, and it happens, and one has to think about clever ways to ensure reliability of the circuits that we're working on. So that again brings circuits, devices, and technologies to the table. So that's quite a bit. I got 5 minutes. That's awesome. So let me leave you with some takeaways. This is what I'm hoping you're still there with me. You know a lot about silicon-germanium now, which is great. Hopefully I have piqued your interest into the world of reliability. It's a very deep and complex and satisfying subject with lots still to be done from a research perspective. So the simple goal for all IC technologies in the world is robust, reliable systems, period. But there's lots of things going on. Device scaling, voltage, current, temperature, variability complicates life, right? As you go to smaller devices, things get harder and harder from a reliability perspective. That's just the facts. And that makes it interesting. Technology, devices, and circuits are tightly coupled. In fact, I think extremely tightly coupled as we look out into the future, right? So meaning if you're a circuit designer and you think you don't need to know devices or technology, you're wrong. If you're a technology person and you don't think you need to know what's happening to the circuits, that's also wrong, right? And you need to come at that coupling from both directions. New operating environments are coming to the table application-wise. That adds lots of complexity. Low temperatures, high temperatures, wide temperatures, space radiation. This is where we want to put our electronic and photonic systems now, and it's fraught with issues to worry about. We need predictive reliability-aware compact models. That's something that many of us are working on. And that will eventually be put, hopefully soon, into the hands of circuit designers to build circuits which are reliable, that occupy this land between classical SOA and hard fill. That'll be a really interesting thing to do. Device reliability is not equal to circuit reliability. So you really need to think about SOA in a different way. That is what I preach to industry, right? They're not the same thing, and they differ strongly, right? Silicon-germanium offers many exciting possibilities. I gave 3 examples, but there's many of those, many more, in fact. Space radiation, SOA boundaries, cryogenic temperatures. But you have to be careful. Silicon-germanium reliability is a nuanced piece, very complex problem, but with lots of financial payoff at the end if you can get your hands around that. And that's kind of what we've all wanted to be doing and what we are doing. So to you students especially, I would say have some fun, forget the conventional wisdom, live on the edge and blow up some devices. And you'll have A, much more fun, and B, you'll probably do more innovative things at the end of the day. Let me leave you with one last thought, and that is to celebrate my team. This is a slightly out of date, but not dramatically out of date picture of my research team. You would be hard pressed to find more capable and hardworking and bright and innovative young people. They are the ones that have done the work that I've shown today. I have a few ideas, yes, but they're the ones doing it in the lab and doing the designs to make these things happen. So let me lift them up. They're a special group of people, and they're responsible for this work. So that's all I had to say. I'm right on time. What I was going to suggest, if there's anybody out there that has a question, unmute yourself and ask it. I am happy to answer anything you would care to know about. Don't ask questions. I'm going to assume that you understood everything I said and agree with everything I said, which is one. But fire away if you have a question. Also, you know how to reach me easily from my email, so ask away there too.
Yeah, thank you, Dr. Cressler. Great presentation. Yeah, for the audience, if you do have questions, you can type them in the Q&A or you can unmute yourself.
Yeah, Gary, I see.
I do have a couple. I do have a couple of questions.
Sure.
So for CMOS transistors, our transistors are shifting from bulk planar structures to FinFET to FDSOI at advanced technology node. So what's the trend for SiGe HBT to further push down the feature size?
That's a good question. So if you look at the state of the art in silicon, well, let me back up for the benefit of everybody there. So CMOS, as you know, is a lateral transport device. And hence lithography drives its performance by and large. And that's why we scale as aggressively in node to get better and better performance. That's why you're at 42 nanometer and below, right? And you move 3-dimension for FinFETs and stuff. For the bipolar, because it's a vertical transport device, it is not nearly so critically dependent upon lithography. It's actually vertical profile that limits its performance. And so if you look at the record-setting technologies today, well, that's in the, approaching 10 nanometer for CMOS, it's up in the 90 nanometer for silicon-germanium at better performance in the silicon-germanium. But it's important to appreciate the more conservative lithography translates to cost ultimately in production. So that gives the silicon-germanium an advantage in that case. So what comes next? I think there is a limit to how far one wants to scale, and part of that actually is not driven by the bipolar, interestingly enough. You've got CMOS on board, these bi-CMOS platforms, and some people need a more aggressively scaled CMOS on there to do, say, DSP that's integrated or whatever, something more sophisticated. So to get the aerial constraints satisfied, you have to go to a more aggressive CMOS. So I've seen people looking today at 45 nanometer, is a sort of a next step type of mode for both technologies. The bipolar will benefit from that, and as well the CMOS. But it's going to 10 nanometer in silicon-germanium doesn't make much sense because it brings to the table all sorts of issues that you don't need to engage because it's not lateral transport limited, right? Does that make sense? So yeah, it's happening, but not the same way. I think the other thing that you're seeing trends in technology is to add more things to these platforms, right? Photonics, MEMS, through silicon via, those are all becoming increasingly routine, I think, and are useful.
Yeah, you also talked a little bit about quantum applications at the end. So what's your opinion for silicon transistors for quantum application? Do you think CMOS or SiGe will dominate quantum computers just like the classical computers we have today?
Yep. So I think there are two camps there, clearly. So if you look in the quantum domain, a couple of things you can say. So both CMOS and silicon-germanium have been shown to operate well in those environments. The natural inclination is that CMOS is lower power and hence better suited, but that's not necessarily true, right? Actually, the bipolar is a very nice low-power RF object. And so if you look at many of the applications, say in quantum computing, those are typically 10 gigahertz or below. And so you can imagine building microwatt RF amplifiers in silicon-germanium for those environments with probably better performance. The I alluded to the variability issue in the silicon-germanium at low temperature. There are reliability concerns there, but I would say those reliability concerns also exist in CMOS. So there's been published data already that there is variability issues at cryogenics in, say, 22 nanometer FDSOI, right? It's a problem out there. Who wins that argument? I don't know. I mean, it's my gut tells me it's kind of like the argument for everything else. You see both today. 20 years ago, people said, yeah, well, CMOS is everything. Don't even build bipolar, but there's still tons of bipolar around and being used in lots of things. I think it's just a matter of what application sphere best suits those devices. And I think, as I said, the silicon-germanium world has been, it tends to be much more prevalent in performance-constrained systems, analog RF, where it's kind of a gold standard for many of these applications. Let's see, can I check chat box? I'm trying to see. Please raise your hand. I've got some Q&A here. Let me just see what we've got here. Great, so any plan to talk CMOS reliability? I would say for me, no, not at the moment. Clearly, when you're talking by CMOS, CMOS reliability is in that table, in that consideration. And I think that's a much more populated field. I would say a couple of things about CMOS reliability, and this is slightly biased from my silicon-germanium perspective. Its physics, to my mind, is a little bit less nuanced than for bipolar, but there's a lot more people working on it. And I would say even these reliability-aware models that I mentioned are more mature in CMOS than they are in bipolar because there's a lot more people working on it, right? So scaled CMOS has its own reliability challenges in just the way that bipolar does, and you will continue to see that, I think. Adrian Ildefonso, who is that guy? Yeah, that's one of mine. Good question, Adrian. Let's see, what do you think is going to be the biggest? But he wants to know, I guess I'm sure everybody sees this. So he wants to know what are going to be the biggest questions moving forward in the design of reliable, high-performance electronic systems in a post-Moore world. I'm not quite sure what you're getting at there. If you're talking 3D systems and bringing a third dimension to packaging and integration of things, I think one of the most constraining problems, even before you move into a 3D system, is thermally driven stuff, right? Thermal issues drive both CMOS and bipolar reliability as we speak today, right? As you certainly know, performance, highest RF performance occurs in the bipolar at high bias current densities, not necessarily current, but current densities. And so those are always going to be an issue. So I would say, well, an environment is also the issue. I think we're operating in much more challenging environments. I gave 2 examples of that. I think you will see more of that. Low temperatures, space-based, thermal issues are going to be also important there. Let's see, a separate question here. Silicon-germanium doesn't have any reliability model. It's very challenging for design or any way to build a reliability model. So that's exactly what I was getting at. Silicon-germanium does not have a PDK available reliability model. That is exactly what we're trying to fix. I would say be careful with the CMOS reliability models. They're not as predictive in the ways that I mentioned as you might imagine. So I think the key is not just to have a reliability model, but to have something as predictive that enables the circuit and system designer to go in and tap this range of space, if you would, in the IV plane between, say, SOA and hard fail, right? That's what you really want. And that's a different kind of model than most reliability models that are out there today. So, but you'll see them. I think you'll see them both. Those are both in process as we speak.
John, this question is for me.
Yes, yes.
Yeah, yeah, I'm more from IBGF to Amazon. So we definitely interested in different technology like SiGe and CMOS. We evaluated them, and we found the SiGe is very challenging to evaluate the reliability performance. Yeah, so that's a big challenge for us to use SiGe right now. Even we see benefit from the SiGe, especially for high power.
Yeah. So the reliability is a nuanced problem in silicon-germanium, and I think That's true. And as I just showed you, DC and circuits are very different things, right?
Yeah.
So I think that's, and I think that's kind of why you need to focus on understanding the physics, and that involves TCAD and building reliability aware models of that to capture those nuanced differences. So I think, is it a fundamental problem? No, I think it's a matter of attention, and the foundries that I talk to are absolutely in tune to that and wanting that. And I think what you really want to do, as I mentioned, is not just do the classical model, which is either designed to SOA and lose the performance that you could get, or build the circuit in some regime and then be forced to test the circuit one by one to see if it's reliable, right? That's not what you want. That's not practical.
Mhm.
You think predictive from a modeling perspective, and I think you'll see that it's coming.
Yeah, this is very challenging for us right now. Yeah. Yes, thank you so much for a great presentation. Okay.
My pleasure. My pleasure. Any other questions? So you have my email, or if you can't, just Google me. You can find me quite easily. I'm happy to answer if you want to send me a note. And Tyann, I want to thank you for having me. This was fun. I enjoyed this.
Yeah, no problem. I see Gary and Kaiyuan, they are still raising hand. Gary and Kaiyuan, do you have questions?
Yeah, I just can you say more about why the you said it was the trench isolation that gives the HBT its rad hardness? Can you say more about
So
that?
that's a good question. Let me back up a little bit. It's not the trench itself. It's actually the way you build the epi-based structure. And so the way you build the epi-based structure, meaning you have to move away from a classical bipolar transistor structure into what's known as an epi-based structure, which allows you to integrate the epitaxial silicon-germanium. When you do that, you get several consequences very naturally, which help you in radiation perspective. So forget the germanium. It's not the germanium. You end up with a very, very thin emitter-based spacer, typically no more than about 1,000 angstroms. So very thin spacer, which is a classical weak point for that device. And importantly, underneath that spacer, because of the high doping of the base, you have very high doping right up against that silicon dioxide region. And so if you imagine introducing trap states into a region where it's got very high doping, it immediately confines the damage possibility, right? The volume of recombination is strongly decreased. So that's very important. And then finally, the vertical profile in these multi-100 gigahertz devices is very, very thin. So it's not as sensitive to displacement damage just because there's not much volume there to damage, right? So all three of those things actually sort of add together to produce this total ionizing dose tolerance. Now, as I pointed out, that's not the only side of the radiation picture. You have transient phenomena as well due to heavy ions, among other things. And that doesn't help you there. You've got to go to a different different techniques to mitigate those phenomena, and it's doable within reason, but not certainly
Are those circuit techniques?
What's that?
Are the techniques to avoid the charge collection, the SEU stuff? Are those circuit techniques you mean?
Circuit and device. So it's a good example of the reliability, triad, if you would, right? So let me give you an example. For instance, if I'm in a bulk-based technology and I've got a heavy ion going right through my device, it's very deeply penetrating. So I generate a lot of charge down in the collector substrate junction, which then is sucked into the collector terminal of the device, which gives you large transients, right? If one, for instance, turned the device upside down, I alluded to this, but didn't show you anything in the interest of time. If I turn the device upside down and now operate it collector down, emitter up, I throw away some performance because it's not really designed to build that, to operate that way. But now the volume of collection is dramatically decreased. And so that I can get much better transient response from a radiation perspective doing it that way. So there is a trade-off between single event mitigation capability and transistor level performance. But at the state of the art, the inverse mode transistors are capable of gains above 100 and frequencies approaching 100 gigahertz, right? So there's still very high performance devices. You can build RF circuits inverse mode, et cetera, et cetera. You can go to, by the way, you can go to SOI You can't do, a fully depleted SOI like you can do in CMOS, but you can go to a thick film SOI in a conventional device, and that is done, in fact. That cuts off that collection tail, if you would, but it doesn't completely mitigate the problem because you still have a high transient at the front end of that as the device junctions collapse under the strike. But it certainly does help and is done, right?
So people, did IBM used to make a SiGe on SOI?
Jazz Foundry does that right now.
Okay.
Apple does not. IBM, I mean, it's been done at IBM, yes, while I was there, but it's, not anymore.
Okay, thanks.
You can't do, again, thin film. Thick film is what you have to do in silicon-germanium because you need the collector, the highly doped thick collector, right?
Yeah, of course.
Yep. Any other questions?
All right.
You guys have been.
Since we don't have any other
Yeah.
questions. Yeah, thank you, Dr. Cressler. Really great having you today.
Yeah, my pleasure. It's always fun to talk to folks. So yes. And again, if you have other questions after the fact or something occurs to you, just drop me a note. I'm happy to answer.
Sure.
All right, everybody.
Thank you, everyone.
Yep.
Thank you. Great
Thank you.
presentation. Thank you so much, Jim.
Thanks.
Yeah, thank
Thank
you.
you.
Bye-bye.
Bye-bye.